Now that we have this new operation on matrices called inversion, right? If we have a square matrix that happens to be invertible, then passing from a matrix to its inverse is an operation, a thing you can do to a matrix. We have to ask, what are the algebraic properties of this operation? How does it interact with all of the other matrix operations? So for example, how does the inversion operation relate to itself? In other words, if you do an inverse and then another inverse, what happens? What do you get? Well, this one we actually already worked out when we first thought about inverses. The inverse of the inverse is A itself. So that one was easy at least. What about inversion and scalar product? If you have, say, a scalar R times a matrix A, and you take the inverse matrix of that, what do you get? Well, you might guess that you should get r to the minus 1 times a to the minus 1. This is really a guess because we don't know what matrix exponentials mean, really. Right? This putting a minus 1 up here is just notation for the inverse matrix. But now that we have this guess, we can check if this guess is correct. How do you check if this really is the inverse for r times a? We'll multiply them and see if you get the identity matrix. So if we multiply these two things, this scalar, well, first of all, because matrix multiplication and scalar multiplication are associative, we can erase the parentheses here, like this. Then we can rearrange this multiplication because scalar multiplication and matrix multiplication commute. We can move this scalar over there. You can't, in general, interchange the order of two matrices, but you can switch the order of a matrix times a constant, or times a scalar. So that gives us this, r times r inverse times a inverse, but r times r inverse is 1, a times a inverse is the identity matrix, and 1 times the identity is the identity. So this guess is correct, right? Inspired guess on our part. All right, what about inversion and matrix product? In other words, if we have a product of two matrices, and both of these matrices are invertible, what do you get if you take the inverse of the product? Well, you might guess, in analogy with real numbers, you might guess that you get A inverse times B inverse. Well, let's check if that's right. We can check in the same way that we checked our guess for the scalar product calculation. We can take A times B, multiply it by the thing we think is its inverse, and then check, is this equal to the identity matrix? If it is, then these really are inverses. So what could we do? Well, we could, again, erase the parentheses because matrix multiplication is associative, so it doesn't matter what order you do things in. It doesn't matter how you pair things up to be multiplied. So, right? In other words, you don't need the parentheses to tell you which multiplication happens first. But then what? It seems like if we're going to end up with the identity matrix, the way to make that happen would be to get this A inverse over here in contact with A, because A inverse times A is the identity. But we can't just turn this around. This product right here, we can't assume that these two matrices are commute with each other. We can't assume that matrix multiplication allows us to turn that around, because we know matrix multiplication is not commutative in general. Maybe in special cases, but not in general. So, I don't know, we're kind of stuck here. And, this is decent evidence that this is not the right thing to guess. But how could we use this to improve our guess? Well, you can see the problem here is that A, it's sort of on the opposite side of its inverse, right? The B is sort of in the middle. Wouldn't it be nice if instead of having A inverse here, we had B inverse here? Because then B times B inverse, well, we could make progress. So maybe this was a bad guess. Maybe we should have the B inverse first and then A inverse. Well, let's check this. So this wasn't right. Let's check A times B times B inverse A inverse. Is this the identity? Well, again, we can erase the parentheses because matrix multiplication is associative. So we get A times B inverse times A inverse. But now B times B inverse, that's the identity. So we have A times the identity times A inverse, but A times the identity is just A. So A times A inverse, that's the identity. So there we go. This is right. So the inverse of a product is the product of the inverses, but you have to turn the order around, right? Have to turn the order around. Thinking about matrices as representing linear maps, this makes perfect sense because, right, if we have a linear map, if we have a composition of two linear maps that are both invertible, what is the inverse function of the composition? Right? Well, the inverse function is going to go this way from u to v, and so, right, first you do, oh, sorry, I have these backwards. This should be g composed with h. So what is the inverse of g composed with h? Well, first you do g inverse, and then you do h inverse afterwards, right? So for functions, the inverse of a composition is the composition of the inverses in the opposite order, and so of course this switch looks the same when you pass to matrices, because matrices represent linear maps. So no surprise there, I guess. All right, what about inversion and transpose? So if we have a transpose, what is the inverse of that? You might guess, is it the same thing as the transpose of the inverse? So is the inverse of the transpose of the inverse? Let's check. So we'll take A transpose and multiply it by the transpose of the transpose of the inverse. So this is the product of a transpose is the transpose of the product, but in the opposite order. And now we have A inverse times A, that's the identity, and what's the transpose of the identity? It's the identity. So we guessed right here. What about inversion and addition? So what if we have A plus B, and they're both inverse matrices, and we want the inverse of that? Well, you might guess, maybe it's A inverse plus B inverse. Maybe. We could check, is this guess right? Well, let's take A plus B and multiply it by A inverse plus B inverse and see what we get. Now we have to be careful when multiplying this out because matrix multiplication is not commutative in general, so we can't accidentally reverse the order of anything. So our first product is A times A inverse. Okay, and then A times B inverse. And then B times A inverse, and then B times B inverse. Okay, so what did we get? We get the identity plus AB inverse plus BA inverse plus BB inverse. Sorry, BB inverse is the identity. Is this going to be the identity? Well, almost certainly not. No, not usually. Almost never. So this is not the right thing to guess. And there are two possibilities. One possibility is just this wasn't the right guess. Maybe we should have guessed something else for the inverse of A plus B. The other possibility is there might not be an inverse for A plus B. Right? It's possible that, well, maybe if A is invertible and B is invertible, maybe the sum of them isn't invertible. And actually that's what's happening here. So just as an example, if A is the identity matrix, the 2 by 2 identity, and B is the matrix -1, -1, clearly both of these are invertible matrices, right? A is equal to its own inverse, right? Because if you multiply A by itself, you get the identity, so A is its own inverse. B, on the other hand, is also its own inverse, because if you multiply this matrix by itself, you get the identity matrix. But if you add these two matrices together, what do you get? Well, you get the zero matrix. Is the zero matrix invertible? Definitely not. The zero matrix represents the zero linear map, which is not an isomorphism. So this is not invertible. So what we're seeing here is there's no nice guess for what the inverse of a sum is, because the sum of two matrices might not even be invertible. So there's not going to be any general formula that we can use here, right? So we have to give up. This is very much related to the fact that if you have real variables, say x plus y, the inverse of x plus y is not the same thing as the inverse of x plus the inverse of y, right? In general, the inverse of x plus y, that's 1 over x plus y, you can't really simplify this. So the same thing happens here. There's no nice formula to make things easier here. There isn't for real numbers, and so there isn't for matrices either, right? The situation for matrices is never simpler than for real numbers. It's always more complicated than for real numbers. So if something is impossible for real numbers, it's probably not going to be possible for matrices either. Now that we have all these algebraic properties, we can actually use them. So for example, we could simplify an expression like this. So simplify A inverse times B, the inverse of that, times A times B inverse. So let's see. Let's simplify. Let's work on this part here. So we're going to leave this last bit, A times B inverse. Leave that alone. The inverse of a product is the product of the inverses, but in the other order. So the inverse of B, and then the inverse of A inverse, but A inverse inverse, right? So here we're doing inverses, but these switch order. But the inverse of A inverse is A. So we'll stop. We don't need to write inverse of the inverse here. Okay, well now look, these two A's are sort of in contact, so we can simplify those. So this is B inverse A squared B inverse. And then, well, then what? I mean, it would be nice if we could combine these two B inverse, these two appearances of B inverse, but they're on opposite sides of this matrix A squared, and matrix multiplication doesn't commute. We can't just move this B inverse over there without knowing something special about B inverse. And we don't know anything special about this matrix B inverse. So we can't simplify this any further. We have to leave this the way it is.